So the next clustering method we're going to study is agglomerative clustering. There are two types of hierarchical clustering. The first one is divisive clustering, and the second one is agglomerative clustering, which we're going to discuss here. So divisive clustering is a top-down approach. So it begins with all data points in one cluster. So in the beginning, you assume the entire data set is one big cluster, and then you split the entire data into a set of subclusters, child clusters, okay? And then each child cluster is divided further. So you keep doing this. You begin with one big cluster and you keep dividing it into smaller clusters, okay, until, okay, every cluster becomes one singleton cluster, okay. Singleton cluster means a cluster with only one data, okay. So that's divisive clustering. It's a top-down approach. So agglomerative clustering is going the other way. Okay, it begins with the bottom and go all the way up to the top. Okay, so bottom up approach. So in the beginning, okay, you assume each data point is a singleton cluster. So in the beginning, each data now becomes a single cluster. Okay, and then you keep merging the most similar nearest clusters. So in the beginning, every data is one single cluster, okay? And then now you keep merging similar clusters, okay? So you keep doing this until you have only one big cluster which contains entire data, okay? So you keep doing this merging, okay, until all data points are merged into a single cluster. So that's agglomerative clustering. So divisive clustering is top-down approach and agglomerative clustering is bottom-up approach. Here we're gonna study agglomerative clustering. Dendrogram is a way of representing the process of hierarchical clustering. So this is the example of dendrogram. So as you can see here, each dot here is a data, and in agglomerative clustering, so each node is a cluster, and you keep merging this, okay, like this. So you keep merging these until you have one single big cluster. And divisive clustering goes the other way. So you start with a big one cluster, and you keep dividing it into sub-clusters, right? So all the way down here, and now at the end, each cluster has only one data. Okay, that's divisive clustering. So in hierarchical clustering, actually you can have as many clusters as you want. For example, if you need 4 clusters, then in dendrogram, if you draw a line here, you're going to have 4 clusters. And if you need 2 clusters, then you draw a line here, then you're going to have 2 clusters. So one advantage of hierarchical clustering is you can have as many number of clusters as you want. About the strengths of hierarchical clustering, the first one is I mentioned in a previous slide. You're going to have any particular number of clusters by cutting proper level at the dendrogram. So as you can see in the example in the previous slide, you can have as many clusters as you want by cutting somewhere proper place in the dendrogram. Second strength is So once you have a dendrogram, you can interpret that dendrogram as an example of a taxonomies. So taxonomy is kind of a hierarchy of knowledge. For example, in biology, you can have a taxonomy of animals. So is this dendrogram can be interpreted as a taxonomy. Finally, we have a divisive and agglomerative clustering, and actually the agglomerative is much faster than divisive. So here we're going to focus on agglomerative clustering. I'm going to give you a very short introduction of divisive clustering and move on to agglomerative clustering. So in divisive clustering, in the beginning, all data points belong to one single giant cluster. And then next question is which cluster you're gonna divide into two subclusters. So for example, let's say we have these clusters. We are in the middle of clustering, and right now you have two clusters, blue one and red one, okay? And you have to decide which cluster you're gonna divide. So when you do that, actually you choose a cluster with largest sum of square errors. In other words, you choose cluster with largest variance value. Okay, that's the cluster you're gonna divide. So you compute the variance of this, and looks like the variance of this is larger than this. So you choose this one, you choose this cluster to divide, okay? So now you choose this one, and the next question is, okay, so now you split this into two subclusters, then how do you draw a boundary, okay, in this cluster in order to separate these clusters, right? So in this particular example, it looks very simple. You draw a line here, okay, and we have very nice clean two subclusters. But in real data, it's not easy, okay? It's very complex actually. So what you can do is you can use word method, okay, to find the boundary, okay? So in word method, what you can do is you're looking for a boundary line which can reduce, okay, which can reduce the variance value the most. Okay, that's the word method. So you draw a boundary line which can separate you can separate your cluster into two subclusters, and that boundary line reduces variance the most, okay? And that's the word method. So finally, you repeat this step 2, step 3 repeatedly, okay, until you reach the desired number of cluster you want, or every cluster has only one data point. Okay, that's divisive clustering. The second hierarchical clustering is agglomerative clustering. So unlike divisive clustering, this one is bottom-up approach. So let's say we have 6 data like this, and in the beginning, every data is regarded as a cluster, and then you keep merging nearest clusters, okay? So in the beginning, we have a 6 data point and 6 cluster actually, and these two are very close. You merge these together, 1 and 3, and next these two are close, so these two are merged, and then this one and this is merged, okay, and after that, and this cluster and this cluster is merged like this, and finally, and this cluster is merged with this one here, and finally we have one big cluster. And this dendrogram shows the process of clustering. Okay, 1, 3 is merged, 2, 5 is merged. This is again merged with 4, and these two are clustered together, and finally we have one cluster. So this is how the agglomerative clustering works. So agglomerative clustering is more popular than divisive clustering. And this shows the pseudocode of the agglomerative clustering. The algorithm is actually quite simple. So at first, each data becomes a cluster, and then you merge to a closest cluster, okay? And then you update the proximity or distance between clusters, and you repeat this until you have only one cluster. So algorithm is simple, but in agglomerative clustering, we have one big issue, which is, so let's say when you do this, you merge to a nearest to closest cluster, then you have to define the distance between clusters. When you define distance between data, it is simple, it is easy. Okay, you can use whatever Euclidean or Manhattan, whatever, you can simply compute the distance between two data. It's easy. But when you define distance between clusters, we have an issue. For example, here we have two clusters, and let's define the distance between these two clusters. This cluster has 4 data points, and this one also has 4 data points. So when you define distance, it is not easy. Okay, you can define distance between these two, like distance between the centroid of these two clusters, or you can define distance between these two, like distance of this and this, or distance between this and this. So there are many options you can choose when it comes to defining distance between clusters. Okay. So in agglomerative clustering, the key operation is the computation of the proximity or distance of two clusters. There are many options. Okay. So there are many different approaches, and these different approaches, okay, and actually distinguishes the different algorithms. So based on this distance measure of two clusters, you're going to have different result of clustering in agglomerative clustering. Okay, now let's talk about how to define distance between clusters. Okay, let's see the easy case first. When the clusters consist of only one data, okay, it's very easy. We can simply define the distance between these two data, and that becomes the distance between clusters. So this is super easy. But in many cases, each cluster has multiple data. Okay, the question is, how do you define the distance between clusters which has more than one data? Actually, we have 4 options, actually a few more, but in this lecture, we're gonna discuss these 4 distance measure: single linkage, or mean, or complete linkage, max, or centroid distance, and the group average. We're gonna talk about this in the following slides. Okay, the third distance measure of cluster is centroid distance. So in centroid distance, the distance is defined as the distance between centroid of each cluster. So here, the centroid distance between the cluster Di and Dj is distance between centroid of cluster Di and centroid of cluster Dj. Okay, this is the definition of centroid distance between these two clusters. The final distance measure is group average. So in group average, the distance is defined as the average of distances between all pairs of data. Okay, that's the definition of group average. So you pick one data from cluster DI, and you pick another data from cluster DJ, and you compute all possible distances, and its average is group average. Okay. And this in group average, actually this one is kind of compromise between single linkage and complete linkage. And its strength is this is more robust. Okay, it's more robust to noise and outliers. And if you use group average, this one tends to generate more globular or ball-shaped clusters. So this is definition of group average. The group average between cluster DI and DJ is so again X is from DI, Y is from DJ. You compute all possible distance between X and Y, okay, and its average is defined as the group average measure between cluster DI and DJ. This picture explains the difference between different distance measure of clusters. So in a mean single linkage, so let's say we have two clusters, okay, and if you use single linkage mean, the distance between these two clusters is this one, this red line, okay, the most closest members, distance between the most closest members, okay. That's the distance between these two clusters. If you use a complete linkage max, this black line is the distance between these two clusters. If you use complete linkage max, okay, again, the distance is defined as the most distant distance of the most distant members, like this. If you use centroid distance, then this is the centroid of this cluster, and this is centroid of this cluster. So the distance between these two centroid is the definition of centroid distance here. If you use a group average, actually you compute distance of every possible pair. Okay, for every possible pair, you compute distance, and the average value of all this distance is defined as the group average. So this shows that the difference between all these distance measures. This one shows an example of agglomerative clustering using a single linkage. So in the beginning, we are looking for distance 1, okay, so this is distance 1, very closest, 11, 12, and 12, 13. So this becomes one cluster, okay. Also, there is a distance 1 here, 8, 9. So these are merged, and these are merged, okay. And then we are looking for distance 2. So let's take a look at, we have this cluster, okay. This cluster has 8, 9, 2 data. This cluster has 3 data, 11, 12, 13. The distance between these two clusters is 2, because we are using single linkage. Single linkage means the distance between cluster is the distance between nearest members, right? So we have one cluster here, you have another cluster here. So distance between these two clusters is the most closest one, 2, 9, 11, okay? So their distance is 2, okay? So this is a distance 2, you merged here because their distance is 2. Here we have another distance 2 here, so 1, 3 is merged, and 3, 5 is also merged. So we have, this becomes one cluster, this whole thing becomes one cluster, and again you have a distance 2 here, we merge here, we merge here, okay? And now in the distance 3 case, let's take a look at this cluster and this cluster. Again, we are using single linkage. So the distance between this cluster and this cluster is distance between these two, which is 3. Okay. So this one, for this one and this one, their distance is 3. So we merge here. So you repeat, okay, all the way to top. So finally, everything will be one cluster. So this is, again, this is example of using agglomerative clustering with single linkage. The next clustering algorithm you're going to study is expectation maximization algorithm. So we have learned k-means algorithm earlier, and the EM algorithm we're going to study here is actually a more general case of k-means algorithm. So both algorithms have their similarity and dissimilarity. The similarity between these two is both algorithms consist of two steps, expectation step and the maximization step, okay? And the difference, the similarity between these two algorithms are these. So k-means it's a hard clustering. That means clusters do not overlap, okay? So for every data, so that data either belong to or it doesn't. Okay, it can belong to only one cluster. Okay, that's hard clustering. But on the other hand, in EM, it's soft clustering. That means clusters may overlap, and actually every data point can belong to every cluster with different probabilities. Okay, so that's a soft clustering. Every data actually belongs to every cluster to some degree. That's a soft clustering. Hard clustering, each data belongs to only one cluster. Okay, that's hard clustering. It's 0 or 1. So because of this hard clustering, this k-means has some problems. So it doesn't do well with overlapping clusters because it is hard clustering. And the clusters are easily pulled off center by outliers. If there are some outliers, it pulls off the data, the center of cluster. Okay, that's the problem of k-means. And each record is either inside or outside of given clusters. So it cannot go both ways. Okay, because of this hard clustering, each record is inside or outside. It cannot go both ways. Okay, that's another problem of k-means algorithm. EM algorithm is based on Gaussian mixture model. So in mixture models, we assume each cluster is a parametric probability distribution, such as Gaussian distribution. So each cluster is Gaussian distribution. It can be any other parametric distribution. By the way, if you use non-parametric distribution in mixture model, you cannot use EM algorithm. And we also assume this cluster, this probability distribution actually generate data. Okay, so these are the assumptions in this mixture model. So because you are using a parametric distribution, each distribution has parameters. So if you use Gaussian distribution, that means this Gaussian has mean and variance. These are parameters of distribution. And again, we are working on soft clustering. That means each data belong to different clusters with different probabilities. So in a Gaussian mixture model, the way you generate data is the following. you choose one of the K Gaussian distribution. Okay, so there are multiple K Gaussian distribution, and you choose one of them. Okay, and then you generate data randomly. Okay, according to that particular Gaussian distribution. So you choose one one of the K Gaussian distribution, and that Gaussian distribution generate data, okay, randomly. So let's say you choose this Gaussian, and then you generate data out of this distribution Gaussian. Then probably the generated data it will be near this mean value, okay. Some will based on the value of variance, some will be off the mean, but most likely the data will be generated around the mean value. So that's how you generate data, okay, in Gaussian mixture model. By the way, when you choose a Gaussian distribution, you can choose with uniform probability. So in this case, each Gaussian has the same probability of being selected. But some other times, maybe each Gaussian has different probability of being selected. So it can be non-uniform probabilities. So that was a short introduction of a Gaussian mixture model. So we are working on clustering. Okay, so clustering is we have to determine which data belongs to which cluster. So right now we don't know the distributions. What we have is the data, and we do not know the source. Okay, which data belongs to which Gaussian we don't know. Okay. The good news is if we know the parameters of Gaussians, then we are able to estimate whether certain data is more likely to be which Gaussian. So we have data only, okay? We don't know anything about the Gaussian distributions. But good news is if we somehow know the parameters of Gaussians, then we are able to estimate, okay, a certain data belongs to which Gaussian with which probability, okay? So that's what we can do. So the goal now is to estimate the parameters of Gaussians. So in EM algorithm, actually what EM algorithm does is it automatically discovers all parameters for the K Gaussian distributions. That's what EM algorithm does, okay? So you're gonna see some example of this estimating parameters of Gaussian in the next slide. This example shows that if we know the source of data, we can estimate the parameters of Gaussian distribution. And also, if we know the parameters of Gaussians, then we can estimate the source of data. Okay, these are the examples. And actually, this is the basic concept of EM algorithm. So suppose we have data x1 or xn, and there are two Gaussians A and B, and their parameters are unknown. Okay, in this case, parameters are mean and variance. So in the first case, if we know the source of data, okay, so if you look at here, these are data, and we know, so we assume we know the source of data. This data belongs to yellow, which is Gaussian A. So yellow, 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 and this one is blue, means this belongs to Gaussian B. Okay, B is blue. Okay, this belongs to B, and this belongs to A, etc. Okay, so if we have data and we know the source of data, then we can easily compute the parameters of Gaussian by doing this. Okay, this is just easy high school calculus. So for the case of distribution B, its average mean is summation of x divided by number of data, in this case 5, very easy. And variance, again, is by definition of variance, it's a summation of square of difference between x minus the mean value, which is given here, okay? And this summation is divided by number of data, 5 here, okay? So this is very simple high school thing. So if you know the source of data, you can easily compute the parameters of each Gaussian. Okay, easy stuff. So in the second case, now we have data, but we do not know the source of data. We do not know which data is from which cluster. Okay, but we do know the parameters of two Gaussians. So even though we do not know the source, we know the parameters of two Gaussians. So we know the exact shape of two Gaussians like this, okay? Then in this case, we can estimate the source of data, okay? So for example, for each data, we do not know the source, right? It's a blank, but we do know the exact shape of two Gaussians like this. So probably this data belongs to yellow Gaussian A, and again, this one belongs to Gaussian A, and this one definitely belongs to Gaussian B, and for this one belongs to a little bit of A, a little bit of B, etc. Okay, so let's compute the exact probability. Okay, so this probability P of B given Xi is, so when Xi data is given, this is the probability that this Xi is from Gaussian B. So this probability is, we have data Xi, okay, and this probability is that this data Xi is originated from Gaussian B, okay. So this probability is this based on base rule, okay. If you remember the basis rule, this is same as this, okay. These two are, if you multiply this both sides, this becomes basis rule, okay. Anyway, so this becomes this, and this one here is, this is the probability that Xi is selected either from A or B, okay. So Xi can be selected either from A or B. So because of that, this can be written as this. This is the case where Xi is selected from B, and this is the case where Xi is selected from A. Okay, there are two cases. X can be selected from A or B. So this is the probability that X is from B, X is from A. Okay. So here, this means you first, when X is selected from distribution B, what's happening here is you select distribution B first, okay, and then within distribution B, this is probability that data Xi is selected from distribution B, okay. The same thing here. You select this Gaussian A first, and within that Gaussian A, Xi is selected, generated from distribution A. Okay, that's what it means here. So these are all cases of where Xi is selected from either A or B. Okay, and this is the case where Xi is selected from B. Okay. So finally, if you compare these two, this is the probability that Xi is selected from distribution B. Okay. So let's look at this prior probability, PA, PB. These are called prior probabilities, and usually for now, let's assume these are same. Okay, uniform probability. So let's assume that these are constant. Okay. For these probabilities, these are given here. So this probability is what? This is used from distribution B. This probability is that the X equals Xi in the distribution B. Okay. This is a simple PDF function from a Gaussian distribution, right? This is very simple, again, high school calculus thing. This is definition of Gaussian PDF, okay? So in a given Gaussian B, this is probability that x equals xi. Okay, you simply plug in x here, xi here, okay? So if you know the value of parameters here, then you can compute this probability, right? If you know these parameters, you can compute this probability, and if you know these probabilities, this, you can compute this. Therefore, you can compute this one, which is the probability that x is originated from Gaussian B. Okay. So in the same way, you can compute the probability p equal p of a given xi, right? So by doing so, you can compute the probability of xi being selected from A or B. Okay. So the example in the previous slide tells us that if we know the source of data, then we can estimate the parameters of Gaussian. Okay. And then if we know the parameters of Gaussian, then we can estimate the source of data points, right? So it goes in circle, and it is like a chicken and egg problem, right? So the basic idea of EM algorithm is we begin with the random initial value of these parameters, okay? And keep iterating these two steps. Then these parameter values gradually becomes accurate, okay, and converge. So that's basic concept of EM algorithm. So EM algorithm consists of two steps, M step and E step. So given a set of data, you have expectation step and maximization step. This is called E step, this is called the M step. So in expectation step, as I said here, using the parameter values, we compute the responsibility. The responsibility is the probability that a certain data belongs to a certain cluster J, certain Gaussian J. Okay, that is called responsibility. Okay, so using the parameter values, you compute responsibility, this one. Okay, that's the expectation step. So each Gaussian has a strong responsibility for points that are close to its mean. So suppose a data is very close to its mean of a certain Gaussian, definitely that Gaussian has very strong responsibility for the data points, right? And the responsibilities, these probabilities, are used as weights in the next maximization step. Okay, I'm going to explain this here. So in maximization step, so in expectation step, we compute responsibility for every data, okay? And then using these responsibility values, I mean these probabilities, now we recompute the parameters of Gaussian, okay? So new parameters are calculated for each cluster, okay, using those responsibility values. So that's the maximization step. So when you compute these parameters, this weight value, these responsibilities are used as the weight. For example, the mean value for a given Gaussian is calculated by averaging all the points. It's weighted by responsibility for that Gaussian. So for example, when you compute the mean of Gaussian, okay, each data is multiplied by the weight values, the responsibility values here. Okay, that is kind of, so responsibility is kind of weight values of data. Okay, that's how it is used here in maximization step. So these two steps are repeated until the Gaussians no longer move, until there is no change in the values of parameter. Okay, so that's the abstract description of EM algorithm. This picture shows the two steps in EM algorithm. So this G1, G2, G3 is the mean of Gaussian, okay? So in the beginning, these are random values, and these are data, okay? So in the beginning, we assume these are the mean of Gaussian distributions. And for every data, for example here, for every data, you compute the responsibility from this data to this cluster, to this Gaussian, okay? So again, in EM, we use soft clustering. That means every data belongs to a different cluster with different probabilities, okay? So you compute this probability from data to cluster, okay? So you compute responsibility for this one, for this one, for this one, okay? So you repeat this for every data, okay? You can say every data belongs to every data in, to some degree, okay? So that's what we do in estimation step, okay? For every data, you compute responsibility, okay, to every cluster. Then for every cluster parameter, okay, you recompute using the responsibility, okay, using all these responsibility values, you recompute the parameter of Gaussian. You recompute the mean value of Gaussian, and you recompute the variance of this Gaussian, okay? So probably this may move to some other place, okay? So that's the maximization step. You repeat this too, okay, until there is no change in the Gaussian, okay? Let's take a look at a little more detail of expectation maximization algorithm. Again, as I said, the EM algorithm is based on Gaussian mixture model, and the Gaussian mixture model has the following parameters. So let's say we have a K Gaussian distributions. K is number of Gaussians. By the way, this K value is given by users. We don't estimate this. And then for each Gaussian J, it has two parameters, mean and variance. So by definition of Gaussian, the probability density of observing data X is defined as follows. Okay, so probability of observing X given this parameter is by definition of Gaussian as defined as follows. And actually each Gaussian has one more parameter called the mixture weight P of J. And if you remember so in Gaussian mixture model, the way you generate data is the following. The first step is you choose one particular Gaussian distribution, right? And then from that Gaussian data is generated, right? So this mixture weight of distribution is the probability that this Gaussian is to be selected. That's the mixture weight of Gaussian distribution. So actually each Gaussian has three parameters, mean, variance, and mixture weight. So put this all together, these are all the parameters we're going to estimate by using EM algorithm. So these are mixture weight of Gaussians, and these are the parameters of Gaussian distribution. Sometimes these mixture weights are predetermined. For example, these mixture weight values are uniform distributions. So in those cases, we don't have to estimate these. We estimate these parameters only. Okay, so it is up to the problems. So anyway, the goal of EM algorithm is to estimate these parameters correctly. The EM algorithm uses maximum likelihood estimation (MLE) method to estimate the optimal values of parameters. So this slide is a very short introduction of MLE method. So MLE is a method of estimating the parameters for maximizing a likelihood function. So you define likelihood function first, and then you want to maximize it. Then by using MLE, you can estimate the optimal parameters which maximize the likelihood function. So in the case of Gaussian mixture model, we know that different values of parameters result in different set of Gaussians. So the goal of EM algorithm is to find the Gaussians that best fit, that best explains or best describe the data by using MLE. That is the goal of EM algorithm. So because EM is using MLE, the first step is to define likelihood function, okay, which is shown here. So this is the likelihood function of EM algorithm, and we're gonna maximize this. And we are looking for parameters which maximize this. That's the actual goal of EM algorithm. And again, the goal is to find the optimal parameters of Gaussian distribution which maximize this. So let's take a look at this. So this is a likelihood function of EM, and we're going to maximize this. So this is probability of capital X given theta. Theta is the all parameters of Gaussian mixture model. We talked about this in previous slide. And capital X means entire data, x1, x2, xn, okay? So this is the probability that this all data, x1, x2, xn, are generated from these Gaussians, okay? These parameters determine one particular set of Gaussians. So this probability is that the entire data x1, x2, xn are generated from these Gaussians. Okay, that's this probability, and this is the likelihood function of EM algorithm. So to be more specific, because we have n data x1, x2, and xn, I said this is the probability that all data are generated from this Gaussian, right? Because we have n data, I equals 1 to n, it's like this. The probability that entire data is generated from this is equal to, this is a probability that x1 is generated times probability that x2 is generated times, etc., and all the way to probability that data xn is generated, right? So because there are n data, this whole probability means probability that x1 is generated times x2 is generated times all the way to a probability that xn is generated, right? That's why we have these n multiplications, and this one here is the probability that one data xi is generated. Okay, so this is the probability that one particular xi is generated from this Gaussian mixture. So when one data xi is generated, it can be generated from Gaussian 1, Gaussian 2, or Gaussian k, right? There are k cases. That's why we have a j equals 1 to k. It can be generated from Gaussian 1, Gaussian 2, or Gaussian k, right? We don't know which one, okay? So for each Gaussian, you compute this probability. Okay, so you suppose j equals 1, then you pick, in this case, p of 1. You select first Gaussian, and then this is the probability that xi is generated from Gaussian 1. Okay. Then move on. If j equals 2, then you pick Gaussian 2, and this is a probability that xi is generated from Gaussian 2. Okay, so for each Gaussian you compute this, and this is the probability that xi is generated from Gaussian j. Okay, so for every Gaussian you compute this, and this one is now the probability that xi is generated, because there are k Gaussians we add together here. So in summary, because there are n data, we have n multiplications. This means probability of x1 is generated times probability of x2 is generated, blah blah, and then probability that xn is generated. So that's why we have n multiplications, and this one is probability that xi is generated, okay, regardless of Gaussian. And then we have k different Gaussian. Because we have k different Gaussian, this one here is probability that xi is generated from Gaussian j. Okay, because there are k Gaussians, we add them together. So that's why this whole thing is the probability that entire data is generated from this Gaussian mixture model. Okay. So this is the likelihood function of EM algorithm, and we are looking for a parameter theta which maximizes this. That's the ultimate goal of EM algorithm. So in practice, when you maximize this, instead of maximizing this likelihood function directly, we usually maximize its log form. We put log both sides here. So instead of this directly, you put log here. The reason is because of these multiplications, the computation is a little tricky. So by using log, this multiplication becomes summation, which makes our computation much easier. So usually we use a log form of this. So the goal of EM algorithm is we are looking for parameter theta, which maximize log form of this. Okay, so argmax theta of this one is this. This one is the log form of this one. Okay, as you can see, this multiplication is now addition. The rest is same. So finally, the EM algorithm, its goal is to find theta parameter which maximize this form. So to solve this problem, actually we don't have any closed form, and we cannot solve this analytically. It's a very complex problem given the amount of parameters. So we use another alternative approach, which is an iterative approach called EM algorithm. So that's the EM algorithm we're going to study here. So the goal is to maximize likelihood function, and we use an iterative approach, EM method, to do that. So I skipped the mathematical derivation part and jumped to the algorithm directly. So in EM, just like k-means, we need to initialize all parameters of Gaussian mixture. And it has two steps, E step, M step. E means expectation. So now we have parameter values. In the beginning, it's randomly initialized. So using these parameters, now we can compute this probability. This is a probability that a data xi belongs to Gaussian j. Okay, so this from basis rule. This is this, and this is the probability that data xi is generated, okay, regardless of which Gaussian. And this is the probability that xi is generated from Gaussian j, okay. So this one becomes this because this data xi can be generated from Gaussian 1, Gaussian 2, Gaussian k. So you do the addition here. And this one is again this probability that xi is generated from Gaussian j. As I said, this means you select Gaussian j first. This is mixture weight, okay, and within Gaussian j, you generate data xi. This is the probability, okay? So again, this P of j is the mixture weight, prior probability, and this one here is within Gaussian j, you compute the probability of xi. This is simple. This is just the definition of Gaussian probability density function, okay? And this one is here is again, this is probability that xi is generated regardless of Gaussian. So we do all this summation here. So the next step is M step, maximization. So after each step is done, now we have this probability that xi is generated from Gaussian j. Since we are using EM for clustering, you can say this is probability that xi belongs to cluster j. So you can say either xi belongs to Gaussian j or xi belongs to cluster j. Okay. So we are EM is using soft clustering. That means each data can belong to different cluster or Gaussian with different probabilities. So for data xi, okay, this belongs to Gaussian j with this probability. So okay, that's soft clustering. So in M step, by using these probabilities, we can re-estimate all parameters of Gaussians. So we have mean, variance. So in mean, this is definition of mean. So we know this value here as a result of each step, and x is given. This is x value. This is given by each step. This is summation of this probability. So actually, this mean of Gaussian j is weighted average of x. So basically, this posterior probability is the weight of data xi. Okay, so mean is its weighted average. The variance of Gaussian j is, this one is given here. Okay, xi is given, already given. Again, this is from each step, and this is summation of this. So variance is by definition, it's again weighted average of the square of difference, right? So you can compute the variance as well. So by using this posterior probability, we can compute mean and variance of each Gaussian or each cluster. That's M step. So in M step, we re-estimated mean and variance of Gaussian. Actually, there are some other parameters, mixture weight of Gaussians. So another step in M step is to re-estimate the mixture weight or prior probability of Gaussians. Sometimes these mixture weight probabilities are predetermined, like these are uniform probabilities. Then you don't have to worry about this. You skip this part, okay, because these values are already determined. If not, then you have to re-estimate these prior probabilities as well. So this is the way we compute, we re-estimate the mixture weight values. So prior probability of Gaussian J is the summation of posterior probability of Gaussian J divided by number of data. So that is the prior probability of Gaussian J. So in M step, we re-estimate mean and variance of each Gaussian. And in addition, if you need to re-estimate prior, then you, by using this formula, you re-estimate the prior probability as well. So we have seen E step and M step. Then we continue doing E step and M step iteratively until there is no change in the values of parameters. So that is EM algorithm. So this is another example of running EM in one-dimensional case. So let's say we have n data x1, xn, and we don't know whether it is from Gaussian A or Gaussian B. Suppose there are two Gaussians, A or B. So yellow one, this one is Gaussian A, and this blue one is Gaussian B. So in the beginning, we randomly initialize the parameters of Gaussian. So mean and variance of A and mean and variance of B. So as I said earlier, by using these parameters, we can compute these probabilities. So this is probability that xi is generated from Gaussian B. Okay, you can do the same in here. This is probability that xi is generated from Gaussian A. Okay, so you can compute this. This is simple definition of Gaussian. Okay, probability density definition in Gaussian. So anyway, in each step, okay, in each step, for each data, you compute the probability that this data belongs to this Gaussian, and also the probability that this data belongs to this. So this is the probability that this xi data belongs to Gaussian B, and this is probability that xi, same xi, belongs to Gaussian A. Okay, so for every data, you compute this probability and this probability. Okay, so if you look at here the majority is yellow. Okay, that means it is this data belongs to Gaussian A with high probability, and this data belongs to Gaussian B with little probability. Okay, small probability. Here, this belongs to Gaussian B with high probability, and this belongs to Gaussian A with very little probability. Okay. So in each step, you compute these probabilities. Okay. So after the each step is done, so this is the result of each step. So now for each data, we compute the posterior probability of each data. So posterior probability means probability that each data belongs to which cluster, which Gaussian, with what probability. So then if you take a look at the Gaussian distribution here, and for blue distribution, for example, most of blue distributions are here, blue data are here. So this blue should move somewhere here, right? And same thing for the yellow distribution, this should move a little to the right, okay? So by using these posterior probabilities, we can recompute the parameters of these Gaussians, okay? So to do that, if you look at the M-step definitions, this is how we compute the mean and the variance of each Gaussian, okay? So for the case of blue, this now moves to this, okay, by using this. And for yellow one, Gaussian A yellow one, again by using this, now this becomes this. Okay, so now we have new parameters, new Gaussian distributions. Now, because we have new parameter, new Gaussian distributions, now we have to recompute the posterior probability of each data. So we have to go back to each step and recompute all this posterior probability of data. Okay, so this is result of each step, and now we have new distributions. So because of this new distribution, we compare this and this, they are changed, right? So for example, for this one strongly belong to Gaussian B, but now it's like half and half, okay? So because Gaussian distribution has changed, this posterior probability has changed as well, okay? So you repeat between each step and M step like this until there is no change. So this is the final result. This is the final Gaussian A and Gaussian B, and this one shows the posterior probability of each data. Okay, how much each data belongs to which cluster or Gaussian. Finally, in M step, if you need to estimate the prior's mixture weight, you can do this by using this formula. But as I said, in many times, some people assume these prior or mixture weights are predetermined, like uniform probabilities or whatever, okay? So in those cases, you don't have to worry about this. This is another example of running EM in two-dimensional case. So suppose these are data and we have two initial Gaussian which look like this. And using these two Gaussian, you compute the probability of each data. So these data mostly belong to this one, this Gaussian, and these data mostly belong to this cluster. Okay. And then that's E step. Then in M step, you have to recompute the parameter of this Gaussian, right? So by using these probabilities, you recompute the parameter of distribution. So this is the result of M step. Okay, this is new Gaussian distribution using these probabilities. Okay, so we have a new distribution here and here. Okay. Now, because you have a new Gaussian distribution, you go back to each step and recompute the posterior probability of each data. So this is the result. Okay. So you repeat. You go back to M step and recompute the parameter of these Gaussians. So you repeat, and at the end, and we have this is final Gaussian form and another Gaussian form. Okay, so which makes more sense. Okay, so this is the final result of EM algorithm.